Okay, the next thing we're going to learn about is vectors, and I thought it would be fun to start by showing you this. This is actually an old record that I have for a band. This actually came out in 1983, and I grew up in the 80s, but I didn't discover these people until I got to college. I bought this at a music festival when I was in college, and it was more than that. I can't remember how much it was, but this must have been the sticker, because you can see it still has the cellophane on it. But Vector, this album's called Mannequin Virtue, and you can see it's like the old records. I don't know how many of you have seen these, but this is when I was growing up in the 80s, we would listen to music on records. Records were still popular. Tapes were coming in. But records were actually better than tapes. Tapes, they broke very easy and they wore out. But records were a little more durable. But one reason for showing you this, the band name is Vector. And I think this is interesting because they have down here, they have the three guys in the band. And I don't know if you can see this. It's kind of light on light here. But right down here it says vector, a change having dimension and direction. And so I guess that's why they called their band Vector. This was their first album. A change having dimension and direction. And that's kind of interesting. But vectors actually, it's not necessarily dimension and direction. The dimension and direction kind of go together, because you could have a two-dimensional vector, a vector in two dimensions, or a three-dimensional vector. And then I suppose there's applications with higher dimensions. We're not going to look at any of that. But basically a vector is it's a quantity that has magnitude and direction. Okay? And some examples of quantities that are like this are displacement, velocity, and force. And these are the main ones we're going to look at. And they're ones that you look at in a basic physics class. And I'm sure there's other vectors as well. But the idea here is these are quantities that have magnitude and direction. So not necessarily dimension and direction, but magnitude and direction. So what do we mean by this? Let me give you an example of displacement. Okay, we could say like here's point A, and some person walked over to point B. Okay, so now they walked a certain distance, okay, but they could have walked that distance in any direction. But the important thing here is they actually went from A to B. And so I could draw an arrow here connecting A and B, okay, and then the length of this, and we'll call this vector V. And what that is that's a V with an arrow up above it, kind of an arrow pointing like that. I don't do the bottom one because I wrote vectors so much. That's just kind of how, or that might be the notation that some textbooks use. So vector V here, it has a length, and that would be the actual length of the arrow, which would be like the distance that the person traveled. And it also has a direction. It's going a certain direction. And so there's like different ways that you can measure this. So I could like give you this angle here. We could call that theta. Okay, and so in a sense it's kind of related. If we represented the vector like this, we would have an r and a theta, right? So it's very similar to polar coordinates. And there's some overlap here. Okay, but we could also say that this when he moved from here to here, maybe he went like 4 miles in one direction and 3 miles in another direction. Or maybe 5 miles in one direction, 3 miles in another direction. Kind of like this. So 5 miles in one direction, 3 miles, or we can say 5 miles east, 3 miles north. And so one way to describe that is to say that it's 5 miles east and 3 miles north or something like that. In which case we could say like vector v, and we're going to use this notation in the next section, is we could say that it's 5 comma 4, or 5 comma 3, very similar to like an ordered pair, but I have these brackets, and that represents the vector here, from here to here. I could also represent this B, A, and then I put the arrow like this, and this is saying that you're going from A to B. So notice the arrow is going this way, and so this here, this is the initial side, and this is the terminal side of the vector. I shouldn't say side. This is the initial point, and this is the terminal point. And so I put the terminal one, the end of the vector first, the initial one second, and then I draw the arrow backwards like this. And then these are all kind of like different ways of representing this arrow. And so we're going to be looking at these. But velocity and force are other examples. Now velocity is like the speed of something, and we might think, well, speed, that's just how fast you go. That doesn't have direction, but you actually go a certain speed in a certain direction. And this is important because like a plane could take off from an airport in a given direction, right? We can say that's the airport, and a plane takes off at 350 miles per hour or something. Okay, but then the wind is actually going in a direction as well. So the wind, I could just say is like this, and maybe the wind is going 75 miles per hour in this direction, whatever direction that is. And so the wind speed and the plane speed are going to come together, and I could put this arrow on the tip of this arrow like this, and then that's actually going to change. It'll go in a slightly different direction at a slightly different speed. Okay? And so when we do something like this, this is called resolving finding the resolvent vector. This would be the resolvent. So if I called this one, let's say I called this V, and I called this one W, then this vector here would be V plus W, and we're going to be looking at that. And so it would be like a resolvent of these two. So velocity, when you're dealing with an actual object moving through space, it does have direction as well. And then force, so force is another example. So like, let's say I'm pushing a lawnmower. Okay, so let's say, hey, that's not a bad lawnmower there. And let's say I'm here and I'm pushing it, okay? And I'm pushing it with a certain force. Now force, you can either have it in newtons, and newtons are, so what is it like, force, if we remember, is mass times acceleration. And so I think newtons are actually, is it kilograms or grams? I think it's kilograms times meters per second squared. And so that's actually, you're taking the mass times the acceleration of something. Oops, move it over. You're taking the mass times the acceleration, and you're getting the newtons, and that's a measure of force. So you're moving a certain mass, and you're changing the velocity of that mass. and so we get these newtons, and we use N for newtons, okay? But you can also use weight here is an example of force, and weight is in pounds, and I can't remember what the units are here, but whenever you're dealing in pounds, you're dealing with a force. Pounds are a certain force working on something in a certain direction. So it's kind of a force is a push or a pull, and it acts on an object. So it's taking and it's moving that object or changing the speed of that object in one direction or another. And so one interesting thing here is if I'm pushing this lawnmower, I'm pushing it forward, okay, but I'm actually pushing down on this. So this vector V is my force vector. And some of that force vector goes down, some of that force vector goes horizontal. So not all of this force vector is being used to move it forward. Only this horizontal component here. And so sometimes it's useful if I'm pushing down on something at an angle, how much is actually going in the direction that I'm moving, in this case, the lawnmower. Okay, so force, velocity, and displacement, those are going to be our main examples. I don't think we do anything besides those, but these are all quantities that have magnitude and direction, and I guess they have dimension too. They said dimension and direction here, and the dimension would be, you could have a three-dimensional vector going from point A to B in a three-dimensional space, not just on a flat surface. Okay. So there you go. That's an introduction here. In the next example, we're going to talk about equivalent vectors and how to tell whether or not two vectors are equivalent.